Hi, good morning everyone. My name is Sushrut and I'm presenting TCS Research Mumbai Lab. Today I'm presenting my work on accurate blood pressure prediction using Korotkoff sound and cuff pressure. So this is a pilot study. I'll first introduce some terminologies and then I'll move on to the work. So first, what is blood pressure? So blood pressure is a pressure exerted by blood on the external walls of the blood vessels when the heart is pumping. What is hypertension? Hypertension is a medical condition when your blood pressure, your systolic blood pressure exceeds value of 140 mmHg or more, and your diastolic blood pressure value exceeds more than that. So it is a life-threatening risk, and it can lead to heart attacks and strokes. So there are two existing methods. There are many methods, but these are the two primary methods. One is the auscultation method, and another is the oscillometric method. So in auscultation method, so this is considered to be as a gold standard method, and in that they use two components. One is stethoscope, and another is a sphygmomanometer. So the stethoscope is used to observe the Korotkoff sound, and the sphygmomanometer is used to inflate there is a cuff which is attached to the upper limb of the arm, and it will inflate and deflate the cuff, which will block the blood flow, and it will after when the cuff is deflated, it will release the blood flow. So when the blood flow is released, there is a certain sound which is called as Korotkoff sound, and the sound when the Korotkoff sound starts, at that time, what is the cuff pressure? That cuff pressure is determined to be the systolic blood pressure, and when the Korotkoff sound stops, at that instance, whatever with the cuff pressure, that will be determined as the diastolic blood pressure. So this is the gold standard method, which has been practiced from 1905. So another method is the oscillometric method. So in this method, it only uses cuff. So basically, when the Korotkoff sound happens, so there is a vibration. Because of that, there is a pressure waves generated in the cuff. So in the whole cuff pressure data, there are small pressure wave oscillations, and they basically take the mean arterial pressure out of that. And there are some proprietary algorithms, and using those formulas or algorithms, they basically calculate the systolic diastolic BP. So there are drawbacks for both these methods. So in auscultation method, because it depends on the physical condition of the operator and the expertise, so you have to observe the Korotkoff sound, and you also have to observe the cuff pressure simultaneously. So it depends heavily on the expertise of the operator, and it may vary from person to person. Also, in oscillating method, since it accuracy relies on the proprietary algorithms, so for some individual or for some instances, it is not that accurate. So why are we doing this? So blood pressure is a very vital indicator for cardiovascular health. Also, according to WHO's report, 2023 report, almost 46% of adults with hypertension are unaware that they have this condition. Why is it hard? Because the actual process of blood pressure measuring, as a for in case of auscultation method, it is hard because it requires simultaneous observation of both cuff pressure and Korotkoff sound. Also, we are making this process fully autonomous and digital without changing the core principle of auscultation method. And why is it important? Because most of the times this manual BP measurement is done incorrectly because of human error or lack of expertise, and because of that, it may lead to wrong diagnosis. Also, the currently existing or commercially, you can say commercially available BP devices, digital BP devices, which are mostly used in home or domicile environment, they are based on oscillometric method, and it is not that much reliable. So this is the proposed blood pressure prediction method. So our research aims to address the subjectivity inherent in the auscultation measurements. And in this blood pressure prediction method, which is based on auscultation method, it has three components. One is the hardware device. So we are using digital sensors such as air pressure sensor and microphone sensor to capture both Korotkoff sound and cuff pressure. We are using CNN model. So basically, this model will classify if this particular sound signal has Korotkoff sound or not, specifically the Korotkoff peak. And the third component is the BP estimation method. So this is completely based on the auscultation method. As I explained, that when the Korotkoff sound starts, at that particular instant, what was the cuff pressure? That pressure will be determined as the systolic, and the point at that particular time instant at which the Korotkoff sound stops. So the start and stop points are determined by the CNN model, and this BP estimation will basically tell you what are the systolic and diastolic blood pressure. So this is the whole BPA prediction method. The goal of the work was it needs to be highly accurate, so more accurate than the existing BP machines. It should be cost effective. So this whole device, we made it in-house and it is very cheap. And it is based on the gold standard method. And lastly, the device should be fully automatic. So this is the hardware device. On the left hand, you can see the block diagram. On the right side is the prototype device. So it is made from simple basic components you can find in any lab. So this was developed on the principle of auscultation, and the sole purpose was just to capture the Korotkoff, good quality of digital Korotkoff sound and cuff pressure simultaneously. So we have used two Arduinos basically to capture the data from signal from the sensors and send it to this system. So I'll explain both the models. First is a digital stethoscope module. In that, the stethoscope, as you can see, the head piece, it is connected to a coupling chamber. So this is just a 3D printed coupling chamber. To in that, there's a microphone sensor. So it is basically the pipe, the head piece is connected to the microphone sensor, and the coupling is used so that there is no environmental noise captured by the microphone. And this microphone is connected to the microphone amplifier, which will basically microphone, what it does is it takes the vibration and convert it to the voltage values, to voltage signals. So these signals are converted from analog to digital using ADC, which is on this Arduino, and we get the ADC signals, which is then stored in the system in a CSV format. In this cuff pressure sensor module, as you can see the cuff. So basically this cuff has two outputs. One pipe is attached to this air pressure sensor. We also have pressure gauge so that we can have a real-time pressure. And then this air pressure sensor basically calculates the pressure in the cuff in the millimeter Hg format, which is how we measure the BP. And it sends to the Arduino, and so Arduino basically stores it in with timestamp to the system. So in the other output of the cuff, it is attached to a digital BP device. So that device is based on the oscillometric method. So there are many cuff-based, oscillometric-based BP devices in the market, and we are using both devices simultaneously so as to validate and compare our BP prediction method. So this is the data representation. This is how the data looks on the right side. The green one is the Korotkoff signal. As you can see, there is a lot of static noise. That is because of the microphone sensor, and there are random peaks occurring at start and end. So basically, if you can see my mouse cursor, so this is the Korotkoff sound, and these are the noise signals. And the red one is the pressure signal. So basically, both the data are captured at the same time instance because it is very crucial for the auscultation method. And to validate this process, what we did was we collected data from 115 subjects under the supervision of medical professionals, which are also the co-author of this paper. Written consent was taken from every single individual. Also, this data collection process was approved by the TCS Internal Ethical Committee. So all the protocols were followed, and the collection process also followed the protocols mentioned under the National High BP Education Program. So what we did was we took 4 samples from each subject. So basically two blood pressure data from left hand and 2 from right hand. So for 115 subjects, we totally took 460 subject data sets. But because of some reasons such as incomplete data or malfunctioning of the system, or if the system is not, or the device is not attached properly, we had to discard some data sets, and we are finalized on 100 subjects. So basically 400 data sets. Among those, 87 are males, 22 are females. So as you can see, this is the gender ratio, and this is the age distribution ratio. All of this was conducted inside our organization's campus and our organization's medical healthcare. So after collecting all this data, we did some pre-processing before feeding it to the CNN model. So basically, as I mentioned, the data set is in the CSV format. So basically, we have one column of ADC values for Korotkoff sound, another column is a timestamp. So first we convert this raw CSV data into audio.wav file using Python library. So why we did it? Because we needed the ground truth before doing all this. So the basically annotations were done by the medical professions, which are also the co-author of this paper. So what we did was, so all the Korotkoff sounds that we have, they listened to it and they basically annotated at what time the Korotkoff sound starts and at what time it stops. Because if you see in this plot, there are many peaks. So you might get confused with if this is the Korotkoff sound or this is the Korotkoff sound. So medical professional is needed to annotate this particular sound. All the annotations were done on all the Korotkoff sounds and all the start and stop time basically. So we are basically getting annotations as a start and stop time, at what time the Korotkoff sound starts and stops. Now the sound signal uh, is converted into split into 1 second time window. Why 1 second? Because the Korotkoff sound frequency is 1 to 1.2 hertz. So the two consecutive Korotkoff peaks, the difference is 1 second. So we are taking 1 second time sliding window with the 60% overlap so that we don't miss any Korotkoff peaks. And this 1 second subsamples, now time domain signals are converted into short time Fourier transform to convert into for a frequency domain, so that we can observe that if this particular 1 second subsample has a Korotkoff sound in it or not, or we can say Korotkoff peak as from the diagram. So after the using that annotations, what we did was we labeled each and every image as 0 as 1. If the image has no Korotkoff peak, then it will label as 0. If it has Korotkoff peak, it will be labeled as 1. And all this is for one Korotkoff sound, right? So we combined all the patients subjects data and created data set. Basically, we having the images and we have labels. So this is how the data pre-processing works. So as you can see in the above diagram, the right side, this is the Korotkoff peak. So as you can see, this is a STFT plot. On the x-axis is the time, y-axis is the frequency, and the z-axis, that is the illumination or intensity, you can say. It shows what is the intensity at that particular frequency. So this peak shows that this is the Korotkoff peak, and on the left hand side, this is the all noisy data. So this is the classification. This is how we labeled images as ones and zeros. And on the below, you can see these are the 1 second time window in sequence. So how the signal works. So this basically 1 second time window, 0 to 1, 0.4 to 1.4, and so on. So basically, we fed all this data into a CNN model. So this architecture was inspired from FPAN works, but we modified these models such as their input layers, fully connected layers, and output layers as per the requirements. We also use data augmentation techniques to make the model highly generalized. Yeah. I'll just finish quickly. Yeah. So basically, in short, we tested this data on the CNN model, and we got the cross-fold validation accuracy of 90%. We also, as the same methodology, we took this 0s and 1s Korotkoff sounds, peaks or images, and we determined at what time instance it starts and stop. And we used the lookup table basically because we also have another CSV file which has the cuff pressure signal with same timestamp. So from that, we point out which is the systolic blood pressure and diastolic blood pressure. So we compared this with the ground truth for both predicted BP values, also for the oscillometric BP devices, and these are the results. And according to the Association for Advancement of Medical Instrumentation, it falls under the acceptable range, which is mean absolute error should be less than, not greater than 5 mmHg, and standard deviation should be less than 8 mmHg. And just to point out that for oscillometric BP devices, as you can see, the systolic for systolic BP, the mean absolute error is much more higher, and these are the error distribution. So the 90%, 95% of errors fall within plus or minus 10 mm range for SBP, and for DBP it is 91%. So conclusion, like to conclude this, this basically shows that after the results, we can be concluded that it is a successfully pilot study. And from this study, we can show that this BP reduction method is non-inferior to the commercial BP measurement devices. And with further developments and refinements, we believe that this could replace the oscillator-based BP devices for domiciliary use only. These are the references. Thank you.